today I would like to present talk entitled Variational Complexity of Functions and Variational Sufficiency in Optimization. This talk is based on the joint work with Dr. Phạm Duy Khánh and Professor Rick Modokovic. Okay, so first of all, I will introduce to you why we have the variational complexity. I will record some local complexity reductions in smooth optimization and maximum monotonicity. And after that, I will give the motivation why we have to study variational complexity. And after that, to study more about the variational complexity, we need some tool of variational analysis, especially second order subdifferential. After that, I will present our results about the variational complexity relationship between the variational complexity and local complexity of the Morrow envelopes, which play a crucial role in not just this property, but also in numerical analysis, numerical optimization. And after that, we will use the co-derivative to characterize the variational complexity, and we will apply the variational complexity to obtain some local optimality condition in composite optimization in section 5 and especially in nonlinear programming. So that is all the outlines I will give you today. Okay, first of all, I will talk about the local complexity reductions and the motivation to study variational complexity. Okay, so here is a classical sufficient local optimality condition. So the sufficient condition to get the local strict local minimizer is we need the gradient equals 0, and we have the positive definiteness of the Hessian matrix. As you can see here, so these conditions will imply the local strong complexity of F around X bar. It's very crucial. It is the condition to guarantee the convergence of some important numerical and optimization algorithms like Newton methods, Radian methods, something. So we have the local strong complexity, so we have great convergence and convergence of these methods. Okay, so it's very crucial. And this reduces convex optimization, so we have a lot of algorithms to deal with this. And the fundamental question here is, do we have sublocal complexity reduction in non-smooth optimization? Regarding the non-smooth optimization, we have the constraint optimization. Do we have sublocal complexity? The answer is the no in general. So for example, we have the NLP nonlinear programming. So we have for example, we have the positive definite of the Lagrange function, but we don't have any local complexity here. That is the things. Okay. And another situation is also in maximum monotonicity. Here is the classical theorem for the function f here. F is convexity. F is convex if and only if the subgradient is maximum monotone. So the subgradient here is made in the sense of limiting subdifferential. The question is, what characterization can be given for the case in which subgradient mapping here is just only maximum monotone locally instead of globally? So what about locally? The answer in the smooth case is positive. In the smooth case, we have the equivalence. F is locally convex around X bar if and only if the gradient mapping is maximum monotone around X bar. But it's not in the non-smooth case. In the non-smooth case, we don't have this. We don't have this equivalence. We don't have the local complexity of the function f here. The simple function is like the absolute value of x minus x squared. So we have the subgradient is locally maximum monotone around 0, 0, but we don't have the local complexity of this function. So the natural questions arise. which property is equivalent to second order sufficient optimality condition in nonlinear programming, non-smooth optimization, something like this. Which property is equivalent to the local maximum monotonicity of subgradient mappings? Okay, that is the question, the answer. We need a property more subtle than the local convexity. So the local convexity cannot characterize these property, right? So this has been answered by Rockefeller, and this property is my mistake. I think that the first one is equivalent to the variational strong convexity, and the second one is equivalent to the variational convexity. This answered by Rockefeller in two papers recently. In here, I list all the paper Rockefeller recently about the variational convexity. Okay, so now the first one. Second, I want to use the tool of variational analysis to study more about the variational convexity. First of all, I need to recall some tool of variational analysis. So I will not discuss more about this because of the time limit. So I don't discuss this. You can find more about this in the book of Modowitz and Rockefeller and West in two books here. And we used the regular normal cone, limiting normal cone, regular coderivative, and subdifferential. It's defined based on the regular normal cone and limiting normal cone. And the second, the one of the crucial tool we use in characterizing is second order subdifferential. It is very natural. So like we define the second derivative is the derivative of derivative, right? So the second order subdifferential is just the co-derivative of subdifferential. Subdifferential is the first order subdifferential. So we have this guy is a second order subdifferential. It's a general line of Hessian matrix. Okay, you have if phi is C2 smooth here, so we have the second order subdifferential is equal to this side. Okay. And the Roth regularity. So Roth regularity is one of the class of function which is generalize the convexity. It's a very broad class. It was introduced by Bolykin and Rockefeller in 1996 in their paper, Roth regular function in variational analysis. There are lots of class of function play crucial role in optimization, cover this, certify this Roth regularity. For example, the function lower C2 function is a map of C2 smooth function, B-square linear quadratic functions, convex B-square linear quadratic function, or convex functions, something like this, B-square linear function. So that is the Roth regular functions. And the subdifferentially continuous is the definition here as one of the function to satisfy this is continuous functions. Okay, it's a major class in the second order variational analysis. And here we move on to the variational convexity of functions. So the function phi is variational convexity if it can be approximated by the function phi here. And we have the localizations of this convex functions. We have the equal of the localization of the subgradient mapping we have here, and the function phi and function psi here is equal in the neighborhood. So this is weaker than the local convexity. This is weaker than local convexity. And when the function psi here is strongly convex, so we have this function is called variationally strongly convex. And some first order characterization of variational convex functions can be found in the paper of Rockefeller. And also he gives some characterization of variational convexity via augmented Lagrange function. Why is it important? Because when we talk about augmented Lagrange function, when we know about the augmented Lagrange method, right? Augmented Lagrange method, we need to solve the subproblem. So the subproblem here, if the function phi here is variationally convex, so the augmented Lagrange function will be locally convex. So when we have the convexity of the augmented Lagrange, so we can solve this problem by using some well-known algorithms like gradient descent, Newton method, something like this. We can solve the sub-problem of augmented Lagrange function. So the hidden convexity in augmented Lagrange function is very crucial. But the key to get this hidden convexity is using the variational convexity. So that is the things. That is why this property is very crucial. And here we will use the Moreau envelopes to characterize the variational convexity. Here, the definition of Moreau envelope here is you can find in the book of Rockefeller, and Rosimo mapping here is a very classical stuff. And here is the theorem, our result. If function phi here is rod-bounded functions, and we have these equivalents. The function phi is variationally convex at x bar for v bar if and only if we have this function here is rod regular, and the Moreau envelope is locally convex around x bar around this point. Okay, why is important? For example, when we want to minimize the function phi, we can minimize the function envelope of phi. The second one is more better. Why? Because the second one, the minimi of the Moreau envelope, we have the differentiabilities of the envelope function. So it's very important properties. When we have the gradient is we have the function is differentiable, we can deal with it easier than with non-smooth function. So, and I think this result can not only important in their own, but it can apply to the Rosimo-Point algorithms. Okay. And here for the variational strongly convex, we have the similar things. If function phi here is variationally strongly convex with this modulus, we also have the local strong convexity of the function phi with this modulus. Okay. And in the case we don't care about the modulus, we also have the equivalent between them. Okay, that's a great result about the Moreau envelope of variational convexity. You can find more about this in our paper. And here we will use the co-derivative or eventually second order subdifferential to characterize the variational convexity. When we have this, we can deduce some second order optimality condition for composite optimization, nonlinear programming, something like this. Okay, for example, here our result is for the function phi non-smooth functions. If phi is a non-smooth function and subdifferentially continuous, and we have this statement, phi is in the classical, you know that phi is convex if and only if the Hessian matrix is positive definite or the whole space, right? But here, variational convex function, here we also have the similarity like this. Phi is variational convex around this point if and only if the second order subdifferential is semi-positive definiteness in this set around this neighborhood. And we have this is the characterization for the variational convexity. The computation for the second order subdifferential is very well. So study you can because we have a full calculus for second order subdifferential, so we can compute the phi when the function phi in a lot of crucial situations. So that is the thing we use this characterization. And similarly, when we have variational strong convexity, so it's equivalent to the positive semi-definite positive definite of the second order subdifferential in this set. Okay, and we also get the Poisson condition for the variational strong convex. Okay, and after that we will apply these results to composite optimization. And here we have some observations. If we have the variational convexity as x bar, we have the x bar is local minimizer. It's similar to the convexity, but the convexity is local minimizer. Here we have just local minimizer. And variational strong convexity, we have X bar is thin stable local minimizer. Thin stable local minimizer is stronger than the strict and strong local minimizer. And definition for the concept called variational sufficiency as follow. The function, we said that if the variational sufficient condition for local optimality, if the function phi is variationally convex at the critical point. Why we need this? If we know this, or if we can characterize the variational convexity at this point, we can give the sufficient condition, and we also give the sufficient condition for the thin stable local minimizer. That's what I mean. And here we will consider the crucial class of composite optimization problem. Here we have minimize the function phi has this form. The function phi has this form appear in a lot of crucial situation in optimization. Not just in optimization, in machine learning, statistics, we have some kind. It's called also cover the Lasso's problem, support vector machine, something. We have this form in optimizations. And the question is, what is the characterization of variational sufficiency in this point? We have, if we know this, if we have characterization of variational sufficiency, we can deduce the second order optimality conditions. Here, okay, here is the characterization. X bar is stationary point, and if we have the condition here, why we have this? Okay, the idea behind here, we will calculate the second order subdifferential of this function. We calculate the second order subdifferential of this function. So, and we get this one, get this condition by calculating the second order subdifferential. Although when you look at this, maybe it's complicated, right? But here we calculate all the components of the function. We can calculate the Hassan matrix, we can calculate the Hassan matrix of G, phi 0, and we can calculate the second order subdifferential of regularization. So all the informations are computed here. Instead of we calculate the second order subdifferential of phi, it is impossible. In this case, we calculate all the components here. And if we have the positive definiteness, and we can get the strong variational sufficiency. And similarly, we also have the point space condition. Okay, and you can see this when we have this condition, we need the full rank condition. So it's sometimes we are very strong, but we want to remove it. To remove it, we need to assume the functions. Well, it's not true for all the non-smooth function. It's not correct for also the special case. Here is we choose the function phi. The function here is strong amenable, and satisfy the first order and second order qualification condition. And we prove that the condition is equivalent to the LICQ condition. And here we LICQ condition in the nonlinear programming. And here we give some condition for when we have the function phi here is strong amenable, we can get the similar characterization as I mentioned before. And the function phi here, here is just the sufficient condition. To get the necessary condition, we need the function phi is be quite linear, or the function phi have this form. And after that, we have the second order necessary and sufficient condition. And finally, we will give the application to nonlinear programming, and we will calculate the function psi in the previous part explicitly. Okay. As you can see that the nonlinear programming has this form, right? So it can be written in the form of composite functions. And here we deduce some result and follow. Here we have the consequence. X bar is a feasible solution to NLP problem, and we have the variational sufficiency at X bar if we have the positive semi-definite of the Lagrange function in the subspace here. Similarly to the strong variational sufficiency, and we have the Poisson condition also. And as you can see in the condition 23, I think it's the new in classical. I'm not sure about this. I think it's new to the best of my knowledge. I identify the second order sufficient condition for local minimizer like this, and the fruit here is based on the second order subdifferential characterization. Okay, that's all the things we get here. For the future investigations, we want to study about the numerical methods that benefit from the local complexity, local strong complexity of Morley envelopes, of variational convex functions. As I mentioned you before, when we have the function phi variationally convex, so we have the local complexity of Morley envelope. So when we can apply this method to Morley envelope, and we can find the local minimizer of the function phi. And implicit characterization of variational sufficiency in more general is polyhedral and non-polyhedral optimization problem. And as you know, when we use we will characterize the variational sufficiency, we need the LICQ condition, because we use the second order qualification condition of that is the things we use chain rule of the second order subdifferential. That is the thing when we want to when we improve this, we want to get the Whittaker qualification condition. So we will use the graphical derivative characterization. When we have this, the constraint qualification of the nonlinear programming will be Whittaker. For example, when we can extend the application to nonlinear programming when we satisfy the matrix subregularity qualification condition. So I think we can use graphical derivative to do this. That is the future investigation. So that's all the things here. Thank you for your attention.
Thank you.